All right, we're going to continue with section 15.2, 15.1, excuse me. I'm going to start with an example, which is find the divergence and curl of the vector field f of x, y, z equals the vector whose I component is 2x, y, z, j component is x squared z, and k component is x squared y plus 1. All right, so first the divergence of f equals, so we take the partial of the first component with respect to x, which is just going to give us 2yz, plus the partial of the second component with respect to y, which gives us 0, plus the partial of the third component with respect to z, which also gives us 0. So our divergence is just 2yz. And we'll talk about the physical interpretation of divergence and curl later in chapter 15. So the curl of f equals, so we have 2xyz and x squared z and x squared y plus 1 I j k partial with respect to x, partial with respect to y, partial with respect to z, and this equals, so we are going to get the partial of this with respect to y is x squared, and then the partial of this with respect to z is x squared. So we're going to get x squared minus x squared in the I direction, and then minus sign for our j component, and the partial of this with respect to x is 2xy minus the partial of this with respect to z, which is also 2xy in the j direction, and plus, now the partial of this with respect to x is 2xz minus the partial of this with respect to y, which is 2xz in the k direction. So we get 0 for all three of our components. So it means we get the 0 vector. All right, so now this next statement we're going to use quite a bit throughout the chapter. So we'll put an asterisk next to this. If the vector field f with components m, n, and p is a vector field defined for every point in space m, n, and p have continuous partial derivatives and the curl of f equals the 0 vector, then the vector field f is conservative. So a couple of things to clarify here. Just this vector field being defined for every point x, y, z in space. So we have to be able to plug in every point in 3 dimensions into our vector field. So we should be able to plug in any point x, y, z without having to worry about whatever dividing by 0 or taking the natural log of a negative number or taking the square root of a negative number, something like that. So it has to be defined on all of 3 dimensions. Then m, n, and p have continuous partial derivatives. So for example, if we look at the previous problem, the problem that we just did up here, this is the partial of p with respect to y, which is a continuous function. It's just a polynomial. This was the partial of n with respect to z, which is it have to have continuous partial derivatives. That's a continuous function. So all these partial derivatives that we see in here are all continuous functions. And then the curl of f is equal to 0. So all of these things here hold for this vector function that we were considering up here. So that tells us that that vector function is conservative. And this is what I was mentioning earlier when I said don't confuse this with the definition of conservative. So a lot of times people think, okay, curl of f equals 0 means that that's the definition of conservative, but not quite. Conservative just means that there is some scalar function f such that this vector field is equal to the gradient of f. So another thing to point out. So also see theorem 15.4 on page 1000. What it states is if the vector field f is conservative, then the curl of f equals the 0 vector. All right, so now let's look at an example. We are going to look at number 19 from your textbook. All right, so we're on page 1003. Next, I'm gonna go to the next page. Should I? All right, so page 1003, number 19. Says in exercises 17 through 24, determine whether the vector function field f is the gradient of some function, some scalar function f. If it is, find such a scalar function. All right, so, and they give us for 19, the vector function or vector field f of x, y, z equals 2xyz. And then, so it's the same vector field we were just working with. So x squared z and x squared y plus 1. X squared y plus 1. All right, so we've already talked about the fact that the partials that these functions are defined everywhere. We can put in any x, y, and z values and we don't run into any issues here. We look at their partial derivatives. The partial derivatives of all 3 of these functions are all going to be continuous, and we already computed the curl of f, and we established that the curl of f was 0. So from our previous example, So the statement right before we did this, said that if all those things hold, then we know that f is conservative. So from our previous example, we know f is conservative. So remember, what does that mean? That means there's a scalar function f such that f is equal to the gradient of f. So that is, there is a scalar function f such that the vector field f is equal to the gradient of f. So that was the first part of the question. It said determine whether f is the gradient of some scalar function f, and we already determined that in our previous example from the things that I just mentioned. So now the second part says find, if it is, find such a function f. So one thing, you don't want to venture off to try to find this f and you haven't established that f exists. So we did establish that by computing the curl, looking at the partials of this, and making sure that these functions all exist everywhere. So you don't want to set out on this lengthy process that we're about to do and then find out it's not going to work. So that's why you first checked those things before you start trying to find your scalar function f. So now, how do we go about finding our scalar function f? So if these two things are equal to one another, then we know the vector field, this thing, has to be equal to that gradient vector. So that tells us that 2x yz, comma x squared z, comma x squared y plus 1 has to be equal to, we know how to compute the gradient. It's just going to be the partial of f with respect to x, comma the partial of f with respect to y, comma the partial of f with respect to z. So the fact we know this says we know this. So now, what does this say? So two vectors are equal if and only if their corresponding components are equal. So that tells us, so f sub x equals 2x y z, f sub y equals x squared z, and then f sub z equals x squared y plus 1. All right, so now how do we go about finding f? So we want f. What we can do is take any one of these partials and integrate it with respect to the same variable. To find f. So that's going to be the start of our process. So you pick any one of these that you want to. So one thing to notice, just depending on your problem, is that if you pick f sub x, you're going to have to integrate this with respect to x. So if this were like 2x times sine x times e to the x, there's no possible way I would want to integrate that with respect to x, because it would be a huge pain trying to do integration by parts over and over again. Then here, say for instance, this one I would integrate with respect to y. That's very easy to integrate with respect to y because there are no y's in there. Here I integrate with respect to z. That's very easy to integrate with respect to z because there are no z's in there. But I may not want to deal with the sum at all. So you pick whichever one of these you want to, and you go for that and you integrate it. So this would be a good time for you to see if you can follow my process, but pick a different one than I pick. Or you can go along with me and then try it again after. So I'm going to go for, it doesn't really matter which one. I'll do the first one. So I'm going to go for integrating this one with respect to x. So f would have to be equal to f sub x, this because this is the derivative with respect to x. If I integrate the derivative with respect to x, if I integrate that with respect to x, that would just give me back f. So make sure you integrate with respect to the same thing you see down here. So for us, that ends up being the integral of 2xyz with respect to x, which gives us, these are just, y and z are just constants, so we get 2x squared over 2, so we just end up with x squared times yz plus, now whenever we do an indefinite integral, we have a constant of integration, but you have to keep in mind what we treated as constants. Constants are, yes, numbers, but as well as y and z, when we're integrating with respect to x, y and z are constants as well. We treated those as constants. So our constant of integration can be a function of y and z. So we can't just put plus c because we were treating those as constants as well. So that would be our constant of integration. So right now, supposedly, the function we're looking for is f equals this thing right here. But that's not good enough for us. We want some more information about whatever this g of yz is. So we're going to take it a step further. Now, at this point, I have squeezed all the information I can out of f sub x. So I can't do anything else with that anymore. Now, any other information I'm going to have to get from these two functions right here. So f is x squared yz plus g of yz. So now, at this point, I have f, and I know how to take partial derivatives. So I'll take a partial with respect to y or z, whichever one you want to, and then of this thing, and I'll set it equal to whatever that is up there. So when I'm going to do with respect to y, if I take the partial of this thing with respect to y, then I'm going to get x squared z plus g sub y of y comma z. G sub y of y comma z. That's when I take the partial of this. But I know from the very beginning that the partial of f with respect to y had better be that thing right there. So now I can set this partial that I found myself equal to the partial that it was supposed to be in the first place to try to find what g sub y of yz is. So we'll put, but we know f sub y must be x squared z. So now we're going to set x squared z equal to this thing. So x squared z equals x squared z plus g sub y of yz. So now these cancel and we get g sub y of yz equals 0. So g sub y of yz equals 0. All right, so now we want to figure out what the function g is because we still have that g right there, and we want to get rid of that and put an actual function in there. I mean, so we want to put in what the explicit function is, so instead of just having g of yz. So now, if we want to find g of yz, we do the same thing we did to find f. If I have a partial with respect to y, I would integrate that with respect to y to find g. So g of yz is going to be the integral of g sub y of yz. I'm trying to get rid of this partial derivative, so I want to integrate with respect to the same variable. So for us though, that's just 0 because that was 0 dy. The integral of 0 is just 0 plus a constant of integration. So usually for us that would be 0 plus c, but we have to keep in mind that we had z here. So really what we're doing is we're treating z as a constant. So we would get 0 plus h of z. This is our constant of integration because we would be treating z's as constants. So now we have g of yz is just h of z. So now we can go and take this and put it back in our supposed f. So we're going to take this right here and we're going to put it back in right there. Because we have g of yz is h of z, so we're going to change that to h of z. So now we have f equals x squared yz plus h of z. And now lastly, we need to find h of z. We've used, though, already. We use f sub x. We use f sub y already. And now we're just going to have to use f sub z. So we're going to take the partial of this with respect to z. The partial of this with respect to z. And use what we know we'll find this and we'll set it equal to that. And then we'll be able to find our h of z. All right, so now taking the partial of what we had in our last line with respect to z, we get x squared y plus the partial of h of z with respect to z is just h prime of z. But we know that f sub z from the beginning of our problem, f sub z is supposed to be equal to x squared y plus 1. So that means this has to be equal to x squared y plus 1. So we have x squared y plus 1 has to be equal to x squared y plus h prime of z. And now the x squared y's cancel on both sides. And we get that h prime of z, has to be equal to 1. So h prime of z equals 1. And then we go through and we can integrate that with respect to z now to try to figure out what h is. And I won't write out this integral. You can if you want to, but because now this is back to single variable calculus where our constant of integration is going to be a true constant, not a function. So, and thus, so when we integrate 1 with respect to z, we're just going to get z plus c. So don't forget about your constant of integration. So thus h of z equals z plus c. And now we're going to take this h of z and put it back in right here. And then we'll have our actual function f. All right, so f is equal to x squared yz plus h of z, which is z plus c. And now we have found our potential function f. And when you're doing a problem like this, you can always check your answer because you can take this function that you have here, take its partial with respect to x, its partial with respect to y, and its partial with respect to z, and make sure you had those original 3 partials that you were supposed to have. All right, so we'll stop this video here and then I'll conclude 15.1 in our next video.